All right, so now we're going to discuss how to measure radiation. And we've got three important factors when we're looking at measuring radiation. Number one is how much radioactive decay there is at a given moment. The transmission factors. So, what is the distance away you are? What type of scattering is there? In other words, what material is it going through? And the absorption of the material. Excuse me. And then the detection. So you've got the source, what it travels through, and the target. All right, so at the source, radiation is measured in becquerels. It is 1 decay per second. All right, so if we have a source, so we got a lump of radioactive material, it's radioactive. And in 1 second, it releases 1, 2, 3, 4 gamma rays. So 4 gamma rays per second. That would be 4 becquerels. And so every second, this radioactive source is releasing 4 gamma rays per second. So 4 photons of gamma radiation coming off this radioactive source. All right, so that is what a becquerel is. Now, it may not be gamma rays coming off. It may be positrons or electrons or alpha particles. So the becquerel is just how many decays per second there are. So this doesn't have any relation to how dangerous it is, because something that's releasing 4 gamma rays per second is a lot more dangerous than something that's releasing 4 alpha particles per second. Something that's releasing 4 alpha particles per second, you put a piece of paper over it, and none of the radiation goes anywhere. If it's gamma radiation, well, you got to cover it in lead before you can contain it. Now, the transmission factors. Okay, so the material, the medium it travels through is important. Right, so if you have something that has, let's say, 4 becquerels of alpha radiation coming off, and it's underwater, well, those alpha particles aren't going to go anywhere underwater. Right, but if those 4 alpha particles are in space, they're going to travel a long ways. So the medium it travels through will affect how much radiation you get. Right, it'll have more effect. The medium it travels through will have more effect on alpha radiation and beta radiation, positrons and electrons, and alpha particles, because gamma rays can travel through like air very well without being absorbed. Now, the distance is also hugely important. Right? So if I'm standing right here, here's me, odds are, according to this diagram, I'm going to get hit by 2 gamma radiations. 2 of these gamma rays. One's going to hit me there, one's going to hit me there. But if I stand way over here, now look, only 1 gamma ray is going to hit me. So distance is very important in how much radiation you receive. There's something called the inverse square law. The inverse square law says something like this. Let's say that I am, so inverse square law. I am 1 meter away and I receive let's say I need a good easy number to work with here. And I receive 64 gamma rays. So okay. So I'm 1 meter away. I receive 64 gamma rays. Now, if I double my distance, if I move to 2 meters away, 2 meters away, I will now receive 1/4 the radiation. So if I double my distance, I will get 1/4 the radiation. So instead of 64 gamma rays hitting me, now it's going to be, whatever 64 divided by 4 is, 16 gamma rays. So just by doubling my distance away, I receive 1/4 the radiation. So this is double distance. If I double my distance, I get 1/4 the radiation. If I triple my distance, I will get 1/9 the radiation, or 1/3 squared. So if I stand 1 meter away and I get 64 gamma rays hitting me, I double my distance, I now have 1/4 the amount of radiation hitting me. And if I triple my distance, I will 1/9 the amount of radiation. So you can see the amount of radiation received goes down very quickly the farther away you get from a source. So the inverse square law is very important. The farther away you get from a source, the amount of radiation received drops off very quickly. Right then, so we've got the source of radioactive decay. It's measured in becquerels, how many decays there are per second. Then the ionizing radiation has these different transmission factors. The distance makes a difference, a big difference. The type of material that it travels through makes a big difference. Then at the end, we get a dose. Now, you can measure it in per second, so like number of gamma rays per second. Or they can do a calculation and figure out sieverts or grays, which take into account how they affect the material they hit. So these guys take into account how they affect right, so we can count how many gamma rays per second hit us. Now, the gamma rays can have different wavelengths, or how many ultraviolet waves hit us per second. But if it's UV radiation, you're going to get a different sievert. So let's say you get like 1,000 ultraviolet waves hitting you per second. That's going to give you a different sievert than 1,000 gamma rays per second. Because UV will do a different, 1,000 UV rays will do a different amount of damage than 1,000 gamma rays. Okay, so sieverts will take into account how they affect the material. Okay, so if you're getting 4 sieverts of radiation, now this is just an example, 4 sieverts of radiation would mean this amount of gamma rays, but it would mean a different amount of ultraviolet rays. Because their frequency is different, their energy is different, they will affect you in different ways. When we're talking about the Rontgens from the Battle for Chernobyl, they're more like this particle count. They're just how many rays hit the detector every second. They don't take into account how they affect the material they hit. Okay, so biological doses are measured in sieverts, right? So 1,000 UV rays is going to give you a different sievert number than 1,000 gamma rays, because 1,000 gamma rays are much more dangerous than 1,000 UV rays. All right, so that's the difference between sieverts and these particle counts. Okay, so 3 things that affect measuring radioactivity: the amount of decays per second, the distance you are to the source and the medium that it travels through, and then the type of measurement that we're doing. You can just count the number of particles, the number of photons, the number of alpha particles, the number of positrons, or you can adjust it for how much they affect what they're hitting with a count like sieverts. Now, we're not in the common doses of sieverts. You know that we have that page at the end that has a whole bunch of different doses of sieverts. Okay, so sieverts is SV. Micro sievert is equal to 1/1,000,000th of a sievert, or which is equal to 0.10ths, hundredths, thousandths, 10,000ths, 100,000ths, that many sieverts. Okay, so when you're reading that chart of common doses, this is what microsievert means. Millisievert, it's like millimeter, is equal to 1/1000th of a sievert, which is equal to tenths, hundredths, thousandths. So it takes 1,000 microsieverts to make 1 millisievert, and it takes 1,000 millisieverts to make 1 sievert. All right, so if you take a look at that chart, here's the radiation chart, and this came from XKCD, I believe. You can see right here is all of the chart by Randall Munro, and there's all the sources right here. You can see 10 minutes, if you spent 10 minutes next to the Chernobyl reactor core after explosion and meltdown, it would give you 50 sieverts of radiation. And fatal dose, even with treatment, is 8 sieverts. And if you remember, those first firemen on the scene at Chernobyl probably weren't that far away from the Chernobyl reactor core after the explosion and the meltdown. They all received fatal doses. No treatment was possible. They all received 8 sieverts, probably some of them within minutes. All right, so you can see here the difference in size, right? A fatal dose is 8 sieverts. An airplane flight has 40 microsieverts. That means 40 out of 1,000,000 sieverts. A dental x-ray has 5 microsieverts. Now, a chest x-ray has 20 microsieverts. All of these blue ones right here fit into 3 green ones. Now, I believe in here there are some other ones from Chernobyl, but I'm not seeing. So if you are a U.S. radiation worker, you are allowed to receive 50 millisieverts. So 51,000ths. Normally, your background dose is 4 millisieverts. So that's how much you normally receive. Typical person normally receives about 4 millisieverts. I'm not seeing any more related to Chernobyl. So you can see here, if you're getting 100 millisieverts a year, that is starting to be linked to cancer. And if you look at all of these green ones together make 75 millisieverts. And if you want to get radiation sickness, radiation poisoning, you're going to need around 400 millisieverts to get radiation poisoning. And if you remember from the video, from the Chernobyl video, radiation poisoning, acute radiation poisoning went vomiting and diarrhea first, and then a latency period. And then after the latency period where you kind of felt all right because your cells were sort of dying off, but they take time to die. Then you started to get these nasty burns, which weren't really burns. They were your cells committing suicide. There was no treatment for those burns. It wasn't hot. It was the DNA in those cells are damaged. And so the cells die. And so deep inside you, cells are just dying. So it's not really a burn anymore. It's just the radiation caused damage to the DNA. Now the DNA commits suicide. Well, on that lovely note, we will end this part of the video.